So what I'm doing here is I'm testing the Haunted Forest board for Wizard of Oz Pinball. I'm testing each LED, we'll call it the pixel. Pixel's got 3 LEDs in it. Each pixel has a red LED, a green LED, and a blue LED. So I'm testing the pixels. I've already verified that the pixels are good with the fluke, and I've also used a bench power supply with current limiting to test the pixels at a lot higher current, and they're fine. The pixels aren't shorted. This board had a blown fuse and a broken electrolytic cap at C126. Yeah, C126. May just be that the broken cap was dangling, and that might be it was intermittently connecting, and that might have taken out the 2 amp time delay fuse. The fuse is soldered onto the board on this thing. So right now I have the fuse out, but I'm running the board on a current limiting power supply. The board normally receives about 7 volts from the pinball machine, so we're running it slightly under 7 volts. The fuse is time delay 2 amp. Right now the current limiting is set up on the power supply for 300 milliamps. That should be low enough to keep the flames to a minimum if something goes wrong here. To test, I put power to the board and watched, and it was only drawing about 15 milliamps idle. So there's no dead short. That's good. But I want to test the control ICs. This board, this Haunted Forest board, controls 12 pixels. And to control 12 pixels, there's 12 LED controller ICs. A6281. It's an obsolete chip. I've got the data sheet here. I've spent quite a bit of time, too much time, reading the data sheet and familiarizing myself with it so that I can quickly do a bench setup to run this board. If I had an Arduino or something like that here, I could program the Arduino to do this for me. It would probably be easier, but I just wanted to do a crude old school bench setup to quickly clock some data into this board and verify that all the ICs are working, because perhaps one of the controller ICs is shorted and it's only going to rear its ugly head when it's active. So I put power to the board with all the control ICs, all 12 of them, idle with no data clocked in, and there's no dead short. So now we're going to need to be comfortable, and so we can sleep, we need to make it so that each one of these controller ICs, U100 through U111, activates its respective pixel, D100 through D111. If we can do that, then I'm going to call it a win. I'm going to assume that the cap probably blew, or that the fuse may have blown because of the broken leg on the cap. I would really be leaning that way, except I don't know, the cap could have got broken when I took the board out and transported it back to the lab. I'm not sure if the cap was already broken or not. I have to admit I did not notice the broken leg on the cap until I already had the board on the bench, and it easily could have gotten, the way that this cap sticks up off the board, it easily could have gotten knocked around. But because this cap sticks out of the board so far, it easily could have gotten hit by the operator of the machine reaching in or reaching around to do something. Easily could have gotten banged on numerous times until that leg finally broke. So we don't know why the fuse blew, and I do know that when I checked Jersey Jack's website, this board, which they're very proud of, judging from the price, the new ones Do have, I've upgraded the fuse to a 3.15 amp time delay versus the 2.0 time delay, which is in this one. They've also added a tiny little daughter board, which I don't know what that's doing. I haven't spent too much time online reading about this. I've spent enough time that I know that apparently these boards have been a sore spot. There's been a lot of failures. The owner of this pinball machine told me that these boards were swapped out early on a couple of times while it was under warranty, but not any more warranty. The thing I have to consider, though, is that this machine's been working for 2 or 3 years with this board. So whatever the flaw is that everybody has made mention to in the brief time I've spent reading the forums, I don't know what it is. And this machine has run for 3 years with these boards, and this is the first one to fail. So if the fuse blew, instead of spending $200 or $300 for a new board, it may be that we can just stick a new fuse in this thing and we're back in business. But for my own personal satisfaction, prior to plugging this thing in with putting a new fuse in it and just plugging it back into the harness and seeing if smoke comes out, I just wanted to play around with it and make sure that each pixel works on the bench prior to plugging it in the machine. So that's what we're doing here. So we're going to clock some data in. I've got the scope hooked up, watching the clock pulses. We're going to go ahead and reset this board by dropping the voltage down again. When the voltage goes low, all the latches and the registers get reset to 0. We go back up to just under 7. Okay. So now when we hit output enable, you see there's no lights coming on. So the next pixel that we're going to test is U107. I've gotten through a bunch of these things now. So we're going to test U107. So the first thing that we're going to do is clock in some data. So I'm going to put in 2 bits, which means I need 2 pulses. So I'm using the burst feature on the signal generator here. I'm going to hold the data line low, and I'm going to clock in 2 pulses. Okay. Now we need to finish off that word. This is Mark.
Mark, it's Mo.
Hey, Mo. Okay. Where did we leave off? We had 2 bits clocked in. I don't remember where we were, so we're going to start again. Okay. So resetting the board by lowering the voltage, bring the voltage back up to about 6, a little under 7, 6.9, a little under 7. Okay, back in business. So 2 cycles, trigger, source. We're going to clock in 2 low bits. There's 2 low bits in. Now we're going to clock in 30 high bits. There's 30 high bits. Okay. Now we're going to clock in. We're going to clock in 32 bits low. And we're going to do that 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 times. Two, 3, 4, 5, 6, 7. release, hit the latch, and there we go. Awesome. Okay, so what we just did is I'm watching the counts up here to make sure that the bits are coming in, the right amount of bits, the right number of bits, because there's a lot of noise. The way I got this thing hooked up is very messy, and a lot of noise is confusing this poor board. And sometimes it doesn't work when I do it. But I'm watching the clock signal to make sure I don't get double pulses or weird noise. I'm counting the bits as they're going in. And so we are at D107. There's D107. That was my next one to test. So we were the signal. So the signal's coming in right here. And because it's a serial data stream going to the shift registers, we have to clock in data for every single chip, just like we were telling Christmas lights to turn on in a row. So in order to get that pixel to light up bright and white, after reading the data sheet, I know that the first bit doesn't matter. The second bit has to be low, and then the next 30 bits have to be high to get the maximum brightness from each of the 3 LEDs in the pixel. And there's another feature in this chip called dot correction and PWM counts, which I'm not even interested in. And if I change the address at the second bit from low to high, then I could play around with that, and that is not my purpose here. But the data sheet is very interesting if you want to read it. A6281 is the number for the control chip, A6281. So I clocked in data that would make any one of these pixels turn on bright white, and then I had to push it through all. I had to push it from here through this guy with lows. Now I could, if I wanted to, I could put any data in the last 30 bits, which would change the brightness on each color of each pixel, but that's not my purpose. My purpose is strictly to turn each pixel on. So I put in the data I need to turn one pixel on bright, and I pushed it through. I pushed it through this one, 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 this one, this one, this one, take it back, this one, this one, this one, take it back. Okay. We went from U100, U101, U102, U U103, U104. Okay, start again. So we clocked in the data necessary to make a pixel go bright white. Then we wanted to push that all the way over to U107. So 32 bits to make, in the correct order, to make a pixel turn on bright white. Which pixel do we want? We wanted pixel D107. So we needed to get the data to U107. So each one of these chips has shift registers. So we had to put the 32 bits to make the thing bright in, and then keep pushing it from one chip to another with 32 bits low, 32 bits low, 32 bits low. Every one of those 32 bits low forced the bright white data to the next chip. So we put bright white data in U100, and then after that we just started pumping in 32 bits low, 32 bits low, 32 bits low. It's 32 bits low, it just leaves the chip inactive. So we put bright white data in U100 and pushed it to U101 with 32 bits low. Then we pushed it to U102 with another 32 bits low. 32 bits low, 32 bits low, 32 bits bright white. Then we put in another 32 bits low, which pushed it to U103. 32 bits low, 32 bits low, 32 bits low, 30, and then bright white. So then we did another 32 bits low to push it to U104, another 32 bits low to push it to U105, another 32 bits low to push it to U106, and another 32 bits low to push the bright white data to U107. Because I've already tested all these ones. I've gone around. I'm going to go around the whole board testing each one. And there it is. We got the data to D107, to U107 to drive D107 bright white. So that tells us a ton. It tells us that every chip in the chain so far from D100 to D107 is working correctly and there's no shorts. So I'm going to go ahead and finish up. There's 1, 2, 3, 4, 5. There's still 5 more pixels to test up to U111. It's monotonous, and I'm sure that there's a million other ways I could have done this quicker. I thought this was going to be quicker, but that's okay. It's fun getting back. And in case you're wondering what's going on the breadboard, we have our data, we have our latch, we have our output enable. And I was originally clocking with a push button and not using the signal generator, but too annoying. Too many bounces, too many false triggers. If the data stream is off by 1 bit, it completely throws you off and you have to start again. So that's what we got. The Haunted Forest board will, I'm sure that all the other 5 pixels and controller ICs are going to be fine. I'm just going to go through the motions. I'm going to replace the fuse. They should be showing up from DigiKey today. And then we'll stick it back in. And it probably was that broken electrolytic capacitor leg that was intermittently making contact and took out the fuse. But that's what we got today, and the next time we'll have something different.